900,000 people are sleeping tonight in the shadow of a mountain that just recorded its largest earthquake swarm in history. Not a metaphor. Not a headline exaggeration. In the summer of 2025, seismic instruments buried beneath Mount Rainier picked up more than 1,000 separate tremors in the span of a few weeks, more shaking than scientists had ever documented at this volcano before. Officials say there is no cause for alarm right now. But if you live in Tacoma, Puyallup, Orting, or Sumner, that reassurance might not feel like enough, because the real danger hiding under Rainier was never the lava everyone pictures when they think volcano. It's something slower, heavier, and far more likely to actually happen. Let's start with what occurred. In the early hours of July 8, 2025, at roughly 1:29 in the morning, seismographs around Mount Rainier began registering earthquake after earthquake in rapid succession, a pattern geologists call a swarm. Within the first 12 hours alone, monitoring teams flagged thousands of possible seismic events, and by the time analysts had sorted through the data, they had located over 1,000 distinct earthquakes tied to the mountain. To put that in perspective, Mount Rainier typically produces around 9 earthquakes a month during ordinary background activity. Swarms do happen here once or twice a year, but they're usually small, lasting a few days and rarely climbing past a magnitude of 2. This swarm blew past every previous benchmark, surpassing even the notable 2009 event in total number of quakes, rate of occurrence, and overall energy released. The strongest single earthquake in the sequence reached only about magnitude 2.4, too weak to be felt by anyone standing on the surface, but the sheer volume of activity was what caught everyone's attention. To their credit, the agencies watching Rainier didn't sit on this information. The United States Geological Survey and the Pacific Northwest Seismic Network published regular updates throughout July and August, walking the public through what was happening in close to real time. And here's the important part that often gets buried under scarier headlines. Despite the record-breaking number of quakes, the volcano's official alert level never moved. It stayed at green, meaning normal, non-eruptive background activity. Scientists explained that earthquake swarms like this are usually caused by hot fluids and gases shifting through cracks and fault lines deep inside the mountain, a routine, if intense, plumbing adjustment rather than a sign that magma is forcing its way toward the surface. By early August, the frequency of quakes had dropped dramatically, falling from dozens of events per hour at the peak down to just a handful of locatable quakes per day. In other words, the swarm calmed down almost as suddenly as it began. So why does a swarm like this matter if nobody felt it and the alert level never changed? Because Mount Rainier isn't just any mountain. It's one of the handful of volcanoes worldwide classified as a decade volcano, a designation reserved for peaks with a history of dangerous eruptions sitting dangerously close to large population centers. Rainier towers over the Puget Sound region at more than 14,000 feet, visible from Tacoma, Seattle, and even parts of southern British Columbia on a clear day. Hundreds of thousands of people live, work, and raise families within sight of its summit, often without a second thought about what's happening underground. What makes Rainier unusual isn't primarily its magma, it's its ice. The mountain holds more glacial ice than any other volcano in the Cascade Range, more than a cubic mile of frozen water sitting directly above a core of rock that has been slowly cooked by acidic gases and superheated groundwater for thousands of years. That constant chemical bath doesn't just heat the rock, it breaks it down, turning solid volcanic stone into soft, weak clay from the inside out. Combine a mountain full of crumbling internal rock with a massive ice cap perched on top, and you get a geological setup that doesn't need a dramatic explosion to become catastrophic. All it takes is gravity and a weak enough slope. That combination has produced real disasters before, and the evidence is still buried in the ground beneath modern Washington towns. Around 5,600 years ago, a massive section of Rainier's summit gave way in an event geologists now call the Osceola mudflow. Nearly a cubic mile of rock and ice broke free and slid downhill, mixing with meltwater to form a churning slurry that swept more than 60 miles, all the way to the shores of Puget Sound. When it finally settled, it had buried over 200 square miles of land under mud and debris up to 100 feet deep in places, permanently reshaping the landscape and creating the flat valley floors where cities like Enumclaw and Auburn stand today. Centuries later, around the year 1500, a smaller but still devastating collapse on the mountain's west side sent a wall of mud barreling down the Puyallup River Valley, reaching the site of present-day Orting in less than 30 minutes and burying entire forests standing upright. Neither of these events required a violent eruption to trigger. Both came from the same slow, hidden process: hydrothermal weakening turning solid rock into unstable clay until the mountain's own weight did the rest. This type of mudflow has a name, lahar, and it's considered the single greatest hazard tied to Mount Rainier today, more dangerous in practical terms than lava, which tends to move slowly and typically stays contained within the national park's boundaries. A lahar, by contrast, can move at speeds up to 50 miles an hour, barreling down river valleys with the density of wet concrete and the force to flatten homes, roads, and bridges. And crucially, a full eruption isn't required to set one off. A rockslide on a hydrothermally weakened slope can trigger a lahar all on its own, with little or no warning. Researchers with the U.S. Geological Survey use specialized fluid dynamics modeling software to simulate exactly how fast these flows would travel given current terrain and ice conditions, and their calculations suggest a major mudflow could reach the town of Orting in roughly 30 to 40 minutes, with Puyallup following less than an hour after that. The towns sitting in these river valleys, places like Orting, Sumner, and Puyallup, are literally built on the deposits left behind by ancient mudflows. Steep valley walls hem them in on either side, which means there aren't many fast routes to higher ground if another flow comes rushing down. Beyond the immediate danger to homes and schools, a major lahar traveling down the White or Puyallup River channels would have devastating ripple effects across the whole region. Interstate 5 could be severed. Rail lines used for shipping could be destroyed. Hydroelectric dams and regional power infrastructure could be knocked offline. The port of Tacoma, a major hub for West Coast shipping, could be forced to halt operations for months. It's not just a local emergency, it's a regional economic one. Given stakes like these, it's no surprise that Mount Rainier is one of the most closely monitored volcanoes on the planet. Hidden throughout the forests along the mountain's river systems are networks of seismometers listening for the faintest underground tremors, GPS and satellite radar stations tracking millimeter-scale changes in the mountain shape that might signal pressure building beneath the surface, and teams periodically sampling gas from summit steam vents to check for chemical shifts that could indicate magma movement. Perhaps most relevant to the lahar threat specifically are the acoustic flow monitors positioned along river valleys like Tahoma Creek, the Nisqually, and the Puyallup. These solar-powered ground sensors are tuned to detect the distinct low-frequency rumble of mud and debris churning down a valley. If they pick up that signature, the system can automatically alert emergency managers and trigger warning sirens in towns downstream, buying residents precious minutes to reach higher ground. Communities in the shadow of the mountain haven't left it entirely up to sensors and sirens, either. In towns like Orting, evacuation drills for lahar events are a routine part of school life. Children practice leaving their classrooms and following marked evacuation routes toward higher elevation on a regular schedule, the same way students elsewhere might practice for fire or tornado drills. It's a strange kind of normal, growing up rehearsing your escape from a disaster most people never think about, but it reflects just how seriously local officials take the risk, even while the volcano itself sits quiet and green on the alert scale. It's worth understanding just how much ice we're actually talking about, because the glaciers on Rainier aren't a minor detail, they're central to why this mountain is considered so hazardous. Rainier carries 28 named glaciers spread across roughly 35 square miles of terrain, more frozen water than every other glacier in the entire Cascade Range combined. One of them, the Emmons Glacier, is the largest glacier by surface area anywhere in the lower 48 states. Another, the Carbon Glacier, holds the record for greatest thickness in the contiguous United States. These ice fields aren't just sitting there passively, either. They feed 5 major river systems that supply drinking water, hydroelectric power, and irrigation to communities across the Pacific Northwest, and at the summit volcanic heat escaping through steam vents carves out hidden networks of ice caves even as the surrounding glaciers have shrunk by more than 20% since the late 1800s. That shrinkage brings its own set of modern hazards, including sudden glacial outburst floods, where pockets of meltwater trapped inside the ice can burst without warning and send rock and debris rushing down popular hiking corridors. It's a reminder that the mountain doesn't need a swarm of earthquakes or a volcanic eruption to pose a threat. The ice itself is in constant, unpredictable motion. When volcanologists actually sit down and model what a future eruption at Rainier might look like, they don't picture just one outcome, they map out a whole range of scenarios based on differing levels of severity. On the milder end, you'd see small steam explosions near the summit crater, ejecting ash and rock but largely staying contained within the national park's boundaries. A step up from that would resemble something closer to the 1980 eruption of Mount St. Helens, sending an ash column tens of thousands of feet skyward, a plume that, depending on wind direction, could drift toward Seattle or Tacoma, potentially grounding flights at Seattle-Tacoma Airport, straining power grids, and complicating water treatment systems across the metro area. But the scenario that keeps emergency planners up at night isn't really about ash at all, It's an unanticipated collapse on the volcano's already weakened west flank, the same kind of hydrothermally rotted rock that has failed before in the Osceola and Electron mudflows. A failure like that wouldn't need a warning eruption to precede it. It could simply let go, sending a lahar into the Puyallup River Valley in well under an hour and permanently reshaping river courses, roadways, and infrastructure across the region for years to come. Long before modern seismometers existed, the people who lived closest to this mountain had already developed their own understanding of its temperament. Local tribes, including the Puyallup, Nisqually, Cowlitz, Yakama, and Muckleshoot, knew the peak by names like Tahoma or Takabwa, generally translated as Mother of Waters. Oral traditions passed down through generations described a mountain capable of shaking the ground, spewing fire and ash, and sending massive floods of mud through the valleys below, descriptions that align remarkably well with what modern geology has since confirmed about events like the Osceola mudflow. For these communities, the mountain was never just scenery. It was a resource for food and medicine in its lower meadows, a spiritual landmark treated with deep respect, and a geographic anchor for trade routes connecting the interior Cascades to the shores of Puget Sound. That relationship with the land shifted dramatically in the mid-1800s, when treaty negotiations forced tribes to cede millions of acres of their ancestral territory to the federal government, even as certain hunting and fishing rights were preserved. Despite that upheaval, the cultural connection to Tahoma never disappeared, and today tribal leaders often work alongside park scientists, blending traditional ecological knowledge with modern volcanic monitoring. European awareness of the mountain came far later. British naval officer George Vancouver spotted and named the peak in 1792, but it took nearly 80 years before anyone attempted to summit it. That changed in 1870, when two explorers pushed to the top with the help of a Nisqually guide, and just 2 decades after that, a schoolteacher became the first woman recorded to reach the summit. Interest in the mountain kept growing through the late 1800s, driven first by rumors of hidden mineral wealth and later by pure tourism, as hot springs, mountain lodges, and increasingly accessible trails turned Rainier into a genuine destination. That popularity eventually led to federal protection. In 1899, the mountain and its surrounding wilderness were established as the 5th national park in the United States, a designation meant to preserve the landscape even as visitor numbers climbed into the millions each year. Today, more than 2 million people visit Mount Rainier National Park annually, drawn by wildflower meadows, glacier views, and some of the most dramatic alpine scenery in the country. Managing that volume of visitors alongside a fragile ecosystem and genuine geological hazards is an ongoing balancing act for park officials, one that has included experiments with timed entry systems and evolving traffic management strategies in recent years. But outside the park boundaries, in the suburbs and river valleys where hundreds of thousands of people actually live, the balancing act looks different. It's about zoning decisions, infrastructure planning, and public education, all playing out under a mountain that occasionally reminds everyone it's still very much alive underground, even when nothing appears to be happening on the surface. That's really the paradox at the heart of the Rainier earthquake swarm story. A record number of tremors rattled through the mountain's interior. Scientists monitored it closely and kept the public informed in near real time, and ultimately the alert level never budged from normal. No eruption followed. No lahar was triggered. Life in the shadow of the volcano continued exactly as it had before the swarm began. And yet the event served as a pointed reminder of just how much is happening beneath a peak that, from a distance, looks like nothing more than a beautiful, permanent backdrop to daily life in Washington state. The mountain's true hazard was never really about whether it might erupt with fire and lava in some dramatic Hollywood moment. It's about the slow, hidden transformation of solid rock into weak clay, a process that has already triggered massive mudflows in the past and could do so again with little warning, regardless of what the alert level says on any given day. So the question worth sitting with isn't really whether Mount Rainier will erupt someday. Most volcanologists agree that eventually, on some geological timescale, it will. The more immediate question is how prepared the towns living in its historic mudflow paths actually are for the kind of event that doesn't require an eruption at all, just a slope giving way under its own weight. Between advanced monitoring networks, community evacuation drills, and decades of geological research mapping exactly where past mudflows have traveled, the region has built real tools for buying time when an event does occur. Whether that's enough, given how quickly a major lahar could move once triggered, is a question that keeps volcanologists, emergency planners, and honestly, a lot of residents who've thought about it, awake at night. If this kind of deep dive into the science and history hiding beneath a familiar landmark is something you enjoy, there's more where this came from, so consider sticking around for what comes next.